Eddy current. And we'll see how we can use it for certain things. Let me explain what eddy current is. Let's say we have a metal disc over here that is pivoted at the center, and it is rotating. I can actually draw the metal center much better. This is a metal disc that is pivoted at its center, and it can rotate anti-clockwise. Right over here, within this region, we have placed a strong magnetic field only within this circle. Now, if you wonder, it's very much possible to do it by using two solenoids facing the electromagnet on two sides. This is the phase view of the setup. Let's say the side view of the setup looks somewhat like, so this is the metal disc from the side, which is a cylindrical shape. And we have one solenoid coil over here, and this coil goes up over here. And there is another solenoid coil on the other side. And they are connected to DC supply. It can be also AC supply, but for the time being, to make us understand, let's make it an DC supply. So this region of that exists between the two coils is producing a strong magnetic field. Let's say for the time being, this is the north pole of the coil and this is the south pole of the coil. And this is the side that we're viewing from here. So our eyesight is here. So we're watching the disk from here. So in this case, for this small region, the magnetic fields are going into the page. So I'm getting small cross signs over here to represent the direction of the magnetic field. Now let's try to understand what is happening. Whenever the disk will start to rotate, the electrons of this disk will also start to rotate along with the disk. As the electrons will start to rotate, they're going to cut across these magnetic field lines, and they're going to flow from left to right, because the disk is going anti-clockwise. So this will be the direction of the electrons flowing by. So if we consider the electron flowing in this way through this region of magnetic field, the conventional current will flow in the other way around because of the electrons moving by. If we now apply Fleming's left-hand rule on the conventional current, so try to apply Fleming's left-hand rule on this region. The magnetic field is aiming into the page or into the screen. The middle finger is aiming to the left, so rotate your wrist, keeping your index finger aiming into the page. Rotate your wrist so that the middle finger now start to aim to the left, and the thumb will give you downwards, which means for this part of the metal disc, electrons, as they flow through here, they're going to experience a force downwards, which means now we're going to have a bigger amount of negative charges accumulating on the lower side, and there'll be some shortage of negative charges, or there'll be some induced positive charge produced on the upper side for exclusively this region as the electrons pass by. So this will produce a potential difference within this circular disk part. And to compensate for this potential difference, the rest of the disk is actually free of magnetic field. So there is no magnetic field within the rest of the disk. So electrons will naturally flow out of this part and use the unaffected magnetic field part to travel to this direction. So this is how the electrons are going to travel to compensate for the EMF that is generated over here. Or we can say the conventional current is going to flow in the opposite direction. So let's say the conventional current is going to flow this way. And this will happen for all the other parts of the disk. So conventional current is going to flow from the positive charge to the negative charge. And this will keep on happening through the disk. All of these currents which are produced over here will happen by a lot of electrons, because this is a metal disc. Metal discs always have a lot of electrons. So the current that will be produced will be pretty big. One more thing that we need to consider, although this is a metal disk, whenever the electrons will flow through the metal body, they will definitely collide with the lattice ions, which is the positive ions at the core of the metal piece, and that will produce some heating effect following that, and the power of that heating can be given by B equals to I square R. So try to understand what is happening. The disk was rotating. We introduced the magnetic field over here. Because of the magnetic field, there is an induced EMF within the region of the magnetic field, across the magnetic field. Because of the effect of this produced EMF, the rest of the disk is going to start to flow in some charges to compensate for the potential difference, which will create some strong current that will pass through the metal disk all over. This current that exists within the disk is what we call eddy current. This is what we call eddy current. Now, I didn't define this whole thing in a single definition. I just showed you a scenario how eddy current is produced. And because of the resistance that exists within the metal disk, this eddy current is going to produce a significant amount of heating. Now, where will this heat energy come from? Now, if we try to go for the idea of conservation of law of energy, this heat energy will be coming from the kinetic energy of the disk. Kinetic energy of disk will convert into heat energy by eddy current, which means as long as we keep the magnetic field turned on and the eddy current keep existing, the disk is going to start to heat up and start to slow down, because more of its kinetic energy will be slowly converting to more into its heat energy, and this will essentially slow down the eddy, slow down this metal disk. This is one of the ways to effectively apply what we call an electric brake. So what we call a magnetic brake. So interesting part for this whole idea is that how much strong will be this braking, or how would be the rate of this energy conversion? This is directly dependent to multiple factors. First of all, if you recall the idea of EMF generation, how much EMF will be produced over here, EMF in a certain disk, EMF induced in a certain location was given by minus d phi by dt. So the rate of change of magnetic flux linkage negative to this would give us the EMF of this location using Faraday's law and Lenz's law combined together. So which means if the disk is rotating really fast, the EMF generated will be pretty high, which is going to cause a significantly strong eddy current, and the heating effect, the heating power will also be very high. So if the disk is rotating at a really high speed, we're going to start losing heat at a pretty high amount, pretty high rate. Also, we can also increase the amount of heating by introducing a small magnetic field. If this magnetic field is made pretty strong, we use multiple coils and such. So in that case, this phi would also be large because of a strong magnetic field. Strong magnetic field will give us a strong magnetic flux linkage, because phi is given by B into A. In this case, A would mean this circle area. So let me just label that with green maybe. So this is the amount of area through which the magnetic flux linkage is working. So let's say if this is the area of A through which B is working, the magnetic field produced by these two coils. So if we make the magnetic field stronger, we're going to lose kinetic energy even more rapidly. The third way is that if we increase the area itself, so for example, other than using in this much of a small area, if we use a bigger circle, or these two coils are made even bigger, we're going to start to lose kinetic energy even more rapidly. And not only that, if we can also produce this eddy current, or the rate of kinetic energy conversion, even more rapidly if we introduce multiple solenoids across different parts of this disk. So if we use, let's say, 6 of these solenoids in different parts of this disk, all of them will produce their individual eddy current, and this will produce a very rapid amount of heating. So other than utilizing only one location for magnetic field induction, we can use multiple coils. Now, why is this important, or how is beneficial, or what is the underlying principle for this whole thing to work? The key underlying principle over here is that the entire metal disk cannot be subjected to a uniform magnetic field. Some part of the metal disk should be affected by the magnetic field. Other parts of the metal disk should be unaffected by the magnetic field. What you need to understand that over here, we applied the magnetic field, for example, within this small circle. Here, the EMF was created, and the other spaces, which is outside this circle, this region of the metal disk was utilized for the flow of current. If we introduce a uniform magnetic field across the whole disk, then this eddy current will not exist. Let me show you an example for that so that you better understand it. For example, let's say if we have a disk that looks like this, and it is also pivoted at the center going into anti-clockwise rotation. If we apply uniform magnetic field all across the disk, what would happen in that scenario? If we apply uniform magnetic field all over the disk, in that case, all the electrons as they cut across the magnetic field lines will experience a force towards the center. So in that case, the electrons will start to accumulate on the outer surface. So we'll have higher negative voltage produced on the circumference, and there will be a really strong positive charge produced at the center. And once these two voltages pretty much become saturated, the current flow will stop because there is no return path for the current. If the entire disk is subject to magnetic field, then eddy current will not exist. For eddy current to exist, we have to have certain regions which are subject to magnetic field and certain regions which are free of magnetic field. These parts where the magnetic field is not working provides for the passage for the current to flow by, within which the electrons are not affected by the magnetic field. So this brings us to the idea that for eddy current to work, the entire metal disk have to be affected by the magnetic field in certain regions, yes, in certain regions, no. Affecting the whole disk with magnetic field will give rise an EMF, but that will not give us a continuous current. We need to have certain locations to produce the EMF, and certain other locations should be responsible as conductor, which would be unaffected by the magnetic field and be providing a return path for the current to flow by. So the definition of eddy current can be given in this way. Let me just give you a very basic definition. Have a look. A localized electric current induced in a conductor by varying a magnetic field. A localized electric current induced in a conductor by varying a magnetic field. Okay, here they are talking about the alternate version, but if we take for the Wikipedia definition, let's have a look at this one. Eddy currents, are also called the Foucault's currents, are loops of electric current induced within conductors by changing magnetic field in the conductor according to Faraday's law of induction. Eddy currents flow in closed loops within conductors in planes perpendicular to the magnetic field. They can be induced within nearby stationary conductors by a time-varying magnetic field created by an AC electromagnet, for example, or by relative motion between a magnet and a nearby conductor. I did not show you the first example yet. I mean, I didn't show you how it can be used by alternating magnetic field. I'm going to show you that, no big deal. But I just showed you this part, that when there is a relative velocity, where this is called relative motion. I just showed you in my example by this one, that there is a relative motion between a magnet and a nearby conductor. So for my example over here, we kept the magnetic field uniform, unvarying, and this was rotating, which was cutting across the magnetic field line. So we're having the eddy current produced. If you're trying to find out the appropriate definition for your A2 syllabus, you can look out for the mark scheme. There is a simple way that I can describe it into my words, is that whenever a certain conductor is subjected to a magnetic field, in different locations, whenever there is a localized magnetic field affecting a metal conductor, and the metal disk and the magnetic field are in motion with respect to each other, it produces a current within the metal disc, full stop. This current is what we call eddy current. So the key primary logic is that the magnetic field affects the metal disc in localized way. It means it doesn't affect the whole disc all over. Affecting the whole disc all over will not result in eddy current, which I showed you in the lower disc scenario. So the magnetic field should affect the metal disc locally, and there should be some relative motion between the metal disc and the magnetic field. One of the very practical uses for eddy current is to be used as high-speed brakes, because this kind of devices can be used for high-speed brakes. Oh, sorry. There is one more thing that I forgot to tell you about, is that there is another way, one more way that we can increase the eddy current is by application of this equation, I equals to NAVE. You can choose to increase the N value. For example, if we use a disk that is made up of sodium, then for each atom, you're going to have one free electron. Whereas if we use a disk that is made up of aluminum, for each atom, you're going to have 3 free electrons within the lattice. Definitely, an aluminum disk will produce a much bigger current compared to a sodium disk. Sodium disk is not very good idea because it's butter-like structure. I'm just choosing this material to give you an idea of the difference between number of charge carrier and so. For example, if you use iron, iron in its pure state has, I think, 3 electrons on its outer shell layer, which comes to the localized electron. So iron can give almost nearly as good as current for like the aluminum. And interesting thing is that whenever these type of brakes are usually used, or more commonly used, in electric trains or bullet trains, which use the magnetic levitation. We don't have them in Bangladesh yet. So, but some other countries like Japan, Korea, and Russia, in USA, there are certain trains which work on magnetic levitation, and they go in very high speed, like 200 kilometers per hour, 250 kilometers per hour, 300 kilometers per hour. Whenever they're trying to stop this brake, using friction braking for these things can prove to be very difficult, and it will produce vibration by a high amount. So at very high speed values, they introduce this eddy current braking. Beauty of this eddy current braking is that you can control very precisely how fast do you want to decelerate the vehicle. For example, if you produce a big amount of current through this coil, you will introduce a very high braking. If you introduce a small amount of current through this coil, you will introduce a very slow braking. So the level of deceleration can be very easily controlled simply by controlling the current that flows through this coil. So that actually helps to reduce the velocity of the vehicle in a very comfortable manner. So what they can do, if they're trying to maintain an uniform acceleration, try to understand, if they're trying to maintain uniform deceleration, they're going to start with a pretty slow current when the vehicle is moving really fast, where this disc could be directly attached with the wheel of the vehicle. And at a high speed, if you even apply a very small amount of current, you're going to lose energy pretty fast because of the high fast rate of cutting through the coil. And as the vehicle slowly starts to decelerate, it has a lower speed, so the rotational speed of this disc becomes less and less and less. They can slowly increase the current on this disc to maintain an uniform deceleration. The bottom line is that when the disc is moving fast, you introduce a small magnetic field to produce a fixed amount of slowing or fixed amount of kinetic energy into heat energy conversion. As the vehicle slows down, so the rotation slows down, you can, I'm not going to say proportionally, I'm going to say you can compensatively, if that's the word. I mean, you can pretty much you can increase the current value so that whatever you are losing because of the speed, you can compensate it for the higher current from your coil. So you can maintain an uniform deceleration, which is very important for the comfort of the passengers. I mean, it's not a very good idea if a certain vehicle decelerates in different rates. That's going to give us some back and forth jerking motion, sometimes that can induce nausea and such. So this is a very useful way for stopping vehicles. Now, one more thing that you might wonder, that why is this kind of braking not introduced for other vehicles like basic automobiles and cars? The idea is that cars and automobiles really don't actually go for that kind of speed that they would require electromagnetic braking. That's the first thing. I mean, cars usually don't run at 300 kilometers per hour for half an hour or 20 minutes journey. I mean, they don't do that. They don't have that kind of free movement region for most part of the world. So for them, electromagnetic braking might not be a pretty good idea, but some supercars which are designed to go for a pretty high braking like that, or maybe some for Formula One vehicles who might want to have a really fast braking in this manner, they might have this kind of technology involved, provided it suits their weight and weight ratio, because every gram of weight in a Formula One car is very important. The more you can give up, the faster your car will go. So depending on all the factors, I mean, if your vehicle is designed to run at a pretty high speed for a prolonged period of time, electromagnetic braking can provide to be pretty useful. So that's one way of understanding the electromagnetic, the idea of eddy current. The second concept that we're going to cover.
Sir, এখানে কি relay produce হচ্ছে ম্যাগনেটিক মানে এটা eddy current গুলো?
আরবে বলো স্যার, বুঝি নাই।
মানে eddy current কোথায় produce হচ্ছে?
এই ব্লু কালারের যে কারেন্ট গুলো আছে, the current which is
in the car example, where are the eddy current?
Let's say if you see within the car, let me just draw a figure. For example, let's say this is the top view of the car. I mean, we're looking from the top. So let's say this is the sitting arrangement, and here is the headlights. So the car is moving this way. So let's say this is the front wheel shaft, which is definitely connected in some way with the engine and such. So with the wheels. To make eddy current introduced, we will have to have some metal disc somewhere attached over here, and around this metal disc we can have these coils introduced. And we can introduce the braking by conducting electricity through this magnetic coil, and that disc is going to heat up, absorbing kinetic energy from the whole car without any physical contact. বুঝছো?
মানে the eddy current থেকে যে heat energy produce হবে ওটা ওই যে current থেকে যে আমরা energy দিচ্ছি ওখান থেকে যাচ্ছে না? How is it going to take the kinetic energy?
হ্যাঁ বলতেছি, try to understand logic by logic, step by step. সেটা হচ্ছে the reason the electrons experience the force is because of the cutting of the electrons with the magnetic field. Why does the cutting happen? Because the disk is rotating. So there is a preliminary source of energy available, which is the kinetic energy of the disk. This kinetic energy of the disk is practically bottom line responsible to produce the EMF, which ultimately produces the eddy current and which ultimately produces the heating effect. So if you want to consider the energy conversion, I mean, the overall energy conversion is the kinetic energy of the disk converts into the heating energy of the disk. Because of the eddy current, within the disk slowly will start to slowly heat up. At the same time, it will start to slow down. So delta K loss equals to delta heat energy gain. Make sense?
Oh, yes, sir.
No, I'm not sure if I could satisfy your question. Could you please ask me the question one more time in different words or so?
But I mean, like electrical energy থেকে I thought you like current to like you did current. There's like I don't know how to.
Okay, I understand. You are trying to visualize where does the electrical energy is coming from. Okay, I'll put it this way. The kinetic energy of the coil is responsible to produce the EMF. EMF is basically what? EMF is the driving energy of the charge carrier. So in this case, which are the electrons. So if you want to get an in-between form, the kinetic energy of the coil of the disk converts into the electrical energy of the electrons, which in turn converts into the heating energy of the disk.
I mean, like electrical মানে ইসে থেকে আমরা যে magnetic field produce করার জন্য একটা current আছে না, ওইখান থেকে এনার্জি দেয় না ইউজুয়ালি?
আচ্ছা, না টিপিক্যালি এই এনার্জিটা আমরা ডিভাইসের কারের ব্যাটারি থেকে প্রোভাইড করতে পারি, or we can use an alternator or dynamo which is also responsible to produce this current. I mean, this current can be also drawn from the disk's motion or the car's motion, but ideally the eddy current is not the current that flows through this circuit. This circuit is responsible to produce the magnetic field. This circuit is used to produce the magnetic field, which will produce the eddy current that is within the disk. Eddy current is not leaving the disk. Eddy current is pretty much confined within the metal disk through the parts which is unaffected by the magnetic field. By definition, this is not eddy current. If you wonder where this current is coming from, this current can be either be produced by an alternator from the car's motion, from the car's engine, or it can be directly fed from the battery of the car. Either of this way possible. But this is a current that is not eddy current. Eddy current will be totally confined within the metal disc altogether. The eddy current will not leave from here. And the basic outcome of eddy current is
that. Wait a minute. Like I was, and yeah, I got it. I বুঝছি মোটামুটি, but transformer তাহলে heat loss হচ্ছে না? Where is the মানে তাহলে ওখান থেকে the energy, we're losing energy, and so like যদি eddy current এর জন্য আমাদের like output কম হয়, তখন energy conversion টা কি?
Exactly similar. ট্রান্সফরমার এক্সাম্পলটা একটু পরে আসতাম যে অল্টারনেটিভ ম্যাগনেটিক ফিল্ড দিয়ে আমরা কিভাবে জিনিসটাকে দিয়ে কাজ করি সেটা আমি এখনই দেখাচ্ছি, and then I'm gonna entertain your question. Just give me some time. But I'll get back to your question. আচ্ছা, এডি কারেন্ট দিয়ে আমরা আরেকটা কাজ যেটা করতে পারি সেটা হচ্ছে ইন্ডাকশন কুকিং. So induction cooking also uses the concept of eddy current. Induction cooking কিভাবে কাজ করে? Let's have a look. Let's say we have a metal plate. I have to draw the metal plate like this. So let me just draw a bit of a 3D view first, then I'm going to go for the 2-dimensional versions for this thing. Let's say this is a metal plate, and underneath this metal plate we have a solenoid that will be fed from an AC supply. And drop a switch over here. This is a closed switch. This will be an AC supply, and the metal plate is pretty large. The coil is not as big as the metal plate. Important information. So if I try to draw the phase view, or if we look from top, so we are looking from the top. So this is our eye, and we are looking from here. This is how the figure might look like. Let's say this is a metal disc, so a metal plate, a metal plate, cooking plate practically, and underneath this metal plate, let's say there is a solenoid coil which has a circular radius of this much. Now I'm not actually drawing clockwise and anti-clockwise because we're going to go for eddy current immediately. Within this metal disc, so using this coil, we can send an alternating current over here. So try and understand, whenever the current will start to increase, the magnetic field that will happen for this coil, this is going to be having a shape like that. That's how magnetic field works. There will be higher concentration of magnetic field lines directly above the coil, and there will be lower concentration of magnetic field lines around the coil. So whenever we'll start to provide current to the solenoid coil, the EMF induction means the rate of change of magnetic flux, the d phi by dt, the magnitude of this thing would be far bigger for this region. So we're going to have a bigger rate of d phi over dt because this is dt in the face of the magnetic field lines. Whereas on the other sides, or on the other regions, the magnetic field cutting would not be as much. So these parts would have a less induction. Try to understand this part first. There is a region of the metal disc which is affected by the alternating magnetic field. The center of this magnetic field, the center of this metal disc is being affected by a stronger change of magnetic field because this is directly in the face of the coil, whereas the neighboring regions are not experiencing as much change of magnetic field strength within the same part. So if I try to give you some numbers, for example, let's say as the cycle goes by for an AC supply, when the current increases from, let's say, 0 to maybe 10 ampere, let's say at the core, the phi, sorry, I wrote theta, the phi, let's say, increases from 0 to 100. Whereas on the outside region, so let's say this is the phi, del phi at the center, where let's say this is del phi at the outside, let's say that changes from 0 to 20. So there is a difference of electromagnetic induction amount because of the concentration of the magnetic field lines. Now try to understand logically, is it possible to happen that we have less induction in one location and we have more induction in another location? It logically how possible kina? because of the concentration of the magnetic field lines. Is it possible to happen? See if that makes sense.
স্যার
বলো।
স্যার আগে যে ডায়াগ্রামটা দেখালেন ওখানে তো হচ্ছে আমরা মানে যেমন দুই দিক থেকে দিচ্ছি নর্থ টু সাউথ, তাহলে একটা ম্যাগনেটিক ফিল্ড তো মানে হচ্ছে, কিন্তু স্যার ইন্ডাকশনের ওইটাতে তো হচ্ছে নর্থ সাউথ তো আমরা বাড়াতে পারছি না, মানে দুই দিকে থেকে তো দিতে পারছি না। মানে
আচ্ছা এই সিনারিওতে
ইয়েস স্যার,
হ্যাঁ
মানে
এখানে আমরা দুইটা কয়েল দিচ্ছি না, সো দুইটা কয়েল না দেওয়ার জন্য আমাদের প্র্যাকটিক্যালি কি হবে, আমাদের there would be a stronger field over here and there would be a weaker field over, মানে আমরা যদি দুইটা ইন্ডিভিজুয়াল মানে বলতেছি, আমরা যদি এখানে দুইটা কয়েল প্লেস না করে শুধু একটা কয়েল প্লেস করতাম তাহলে আমাদের এই সিস্টেমটা কাজ করতো, বাট অবভিয়াসলি আমাদের সিস্টেমের এফিসিয়েন্সিটা কম হতো। আমি দুইটা কয়েল দেখানোর মেইন রিজন হচ্ছে বিকজ আই ওয়ান্টেড ইউ টু ভিজুয়ালাইজ দ্যাট দ্য ম্যাগনেটিক ফিল্ড ইজ মানে কি বলবো এটা concentrated within a certain region. If I placed only one field over here, if I placed only one coil, then the natural idea would be that the field lines are going to spread out as they leave from the magnetic field. So সেই কেসে আমাদের এখানে একটা হয়তো একটা ছোট মানে if I didn't draw this thing, this coil, then we would have the spreading of the magnetic field lines like this. So we'd have a smaller circle over here, a larger circle on the back. So this figure, drawing this 2D figure might be very difficult for me. That's why he provided two different magnetic fields. But if I didn't give two different magnetic fields, would still have the magnetic field lines coming from this direction and entering through the coil and coming out over here. So certain part of the magnetic field induction would still be available. Having two fields helps me to explain it better, but using only one field would still do the job because field lines will pretty much travel from right to left through the disk anyway.
আচ্ছা স্যার, তাহলে তো আমরা নরমাল একটা ম্যাগনেট ইউজ করতে পারতাম না?
হ্যাঁ, আমরা একটা বার ম্যাগনেট স্কুল এটা করতে পারতাম, বাট বার ম্যাগনেট স্কুল আমাদের যে জিনিসটা হতো সেটা হচ্ছে আমরা ইচ্ছা মতো এনার্জি কনভার্সন রেটটাকে কন্ট্রোল করতে পারতাম না। আই মিন ইন প্র্যাকটিক্যাল কেসেস লাইক ইন দ্য ব্রেকিং সিস্টেমস অফ electromagnetic trains or maglev trains, they actually physically control the current flow within this coil, control how much rate of energy transfer do you want to have. মনে করো আমরা যদি এখানে একটা বার ম্যাগনেট ইউজ করতাম তাহলে জিনিসটা হতো যে গাড়ি যখন স্টার্ট করতেছে তখন থেকেই আমাদের কি হইতো, আমাদের এই ডিস্কের মধ্যে একটা এনার্জি খরচ হতে থাকতো। তার মানে হচ্ছে when as long as the car is moving, whether you are trying to accelerate the vehicle or you are trying to maintain a constant speed or you are trying to maintain make deceleration, throughout the entire journey this disk will be causing you some energy loss, but which is something that we really don't want, কারণ whenever the vehicle is to be accelerated জিরো থেকে আমরা একটা certain top speed এ নিব, তখন যদি আমাদের visibly একটা এনার্জি লস হয় সেটা আমরা চাই না। We would only want this energy loss to happen when we are trying to brake the vehicle or slow down the vehicle. That's why the electromagnet is very helpful, because as long as you don't flow current through the electromagnet, it is non-existent. The moment you start to flow current, it comes into existence, right?
Yes sir.
মানে বুঝছো ইলেকট্রোম্যাগনেটটা কেন ইউজ করছি, বুঝে গেছে?
Yes sir, বুঝেছি।
ঠিক আছে, যদি আমরা বার ম্যাগনেট ইউজ করতাম বা পাওয়ার ম্যাগনেট ইউজ করতাম তাহলে যেটা হতো ফিজিক্যালি ব্যান্ডগুলোকে বারবার রিমুভ করতে হতো, দূরে সরাইতে হতো, আবার হচ্ছে ফিজিক্যালি ওদেরকে মুভ করতে হতো, so that would require some mechanical movement, and this is always these things can always fail. Whereas an electrical circuit that will be where we will only control the current, this is actually much too simpler to install and also maintain. আচ্ছা, getting back to the induction cooking. So এখানে যে কোশ্চেনটা করলাম যে whenever the current will change in this way because of the differential concentration of the magnetic field lines, a certain region of this cooking plate, metal plate, will experience a bigger amount of change of magnetic flux linkage, and the surrounding area would experience a smaller amount of magnetic flux linkage. Does this idea make sense? Can you logically accept this? যেটা হওয়া পসিবল, দূরের পয়েন্টগুলোতে আমাদের d5/dt কম হবে আর ভেতরের পয়েন্টগুলোতে d5/dt বেশি হবে for the within the same amount of time. এখন যে জিনিসটা হবে সেই জিনিসটা আমরা বুঝাচ্ছি। মনে করো for the duration when we have an increase of the current, or let's say current to the AC supply, to this AC supply the current is increasing from 0 to 10 ampere. Let's say within this direction, within this part, within the central part, let's say at the center, let me write this thing. এটা মুছে ফেলি, এক মিনিট, where is this select? Let's say when the current is increasing to this part, let's say at the center, the EMF at the center increases from 0 volt EMF at the center, let me give just EMF at the center increases from 0 volt to, let's say, plus 50 volt, whereas EMF at the outside, I mean, one thing you need to understand that at different circular part, if you consider different parts, will have different value of EMF generated. So different circles will have different amount of flux linkage change, and they're going to produce different lengths. So if we just only consider one single specific location outside this disk, one single location for the sake of easier discussion, মনে করো এটা হচ্ছে আমাদের কয়েলের ফেসের এন্ড, এটা হচ্ছে আমাদের একটা আরবিট্রারি একটা সার্কেল যেখানে আমরা আলাপ করতে যাচ্ছি। সো এটা মনে করো হচ্ছে আমাদের সেন্ট্রাল ডিস্ক, এটা হচ্ছে আমাদের আউটসাইড ডিস্ক, এটা হচ্ছে আমাদের আউটসাইড ডিস্ক। লেটস সে উইদিন দ্য আউটসাইড ডিস্ক the EMF increases from 0 volt to, let's say, plus 20 volt. এই যে দেখো এখানে আমাদের EMF এর একটা ডিফারেন্স ক্রিয়েট হলো, ডিফারেন্স ক্রিয়েট হলো না? মানে হচ্ছে আমাদের এই পার্টের ডিস্কের মধ্যে, এই পার্টের পুরোটুকুর মধ্যে আমাদের ভোল্টেজ হচ্ছে লেটস সে প্লাস 20 ভোল্ট, সরি প্লাস 30 প্লাস 50 ভোল্ট। let me use a different color so that we can see it better. সো মনে করো এই ডিস্কের ভিতরে হচ্ছে মনে করো প্লাস 50 ভোল্ট, আর এই ডিস্কের মধ্যে আমাদের ভোল্টেজ হচ্ছে প্লাস 20 ভোল্ট। তাহলে এইটুকুর মধ্যে আমাদের একটা 20 ভোল্ট 30 ভোল্টের একটা পটেনশিয়াল ডিফারেন্স ক্রিয়েট হলো। এটা 30 ভোল্ট পটেনশিয়াল ডিফারেন্স জন্য কি হবে? ইলেকট্রিক্যাল কারেন্ট, কনভেনশনাল কারেন্ট উইল স্টার্ট টু ফ্লো আউট রেডিয়ালি। এটা হবে না? কনভেনশনাল কারেন্ট উইল স্টার্ট টু ফ্লো আউট রেডিয়ালি। এটা হওয়া পসিবল কিনা? Or in other words, I can say the electrons, negatively charged electrons, are going to start to flow in radially. Is it going to happen or not? It logically possible kina? Because both of them are positive voltages, but one is a higher voltage than the lower voltage, and current always flows from high potential to low potential. Etar mane hocche for the duration the current increases from 0 to 10 ampere, gradually there will be an increased potential difference between the face of the coil and the outer periphery. So in this case, current is slowly going outwards like an aerial direction. For the next part, when the current will go down, so from 10 ampere it will drop down to 0, then the EMF change will happen this way. So what's going to happen for this part, as the current happens over here, let's say, then the EMF in the center will change from plus 50 volt to 0 volt, and EMF at the outside, that's going to change from plus 20 volt to 0 volt. So there will be a decrease in voltage. So that will cause the current flow to lower. In the opposite cycle, when the current is going to start to increase in the opposite direction, let's say this is the scenario. So this is the opposite half cycle, so negative current. For that scenario, let's say the EMF at the center, or let me use a different color, EMF at the center will increase from 0 volt to, let's say, minus 50 volt. And in that case, the EMF on the outside periphery will increase from 0 volt to minus 20 volt. So one thing that I want you to understand, I'm actually choosing this cycle for my convenience to explain it well, but the EMF will not be changing as is. There will be a 90 degree phase shift. যেটা আমি একটু পরে আলাপ করতেছি, I'm going to discuss this a bit later. For the time, you just try to understand the concept that there will be a gradual change of the EMF. So as the current flow will change back and forth, we're going to have a opposite change of EMF generation, and this EMF generation will cause the central disk to become negative, highly negative, and the outer disk to be less negative. So in that case, the current flow will start to happen from the outside to the inside. Point that I'm trying to show you is that as the coil will keep carrying alternating current, it will produce different magnetic flux linkage variation. All of these words are important. It will cut across a plate differently. So different locations on this plate will experience different rate of magnetic flux linkage change. The rate of change of magnetic flux linkage on this metal disc will be different in different places. As a result, they will be producing different values of EMF, and this difference of EMF will produce a current flow within the metal plate as long as there is a potential difference. This current flow is, in this case, what we're defining as the eddy current, and that eddy current will once again produce heating using the formula P equals to I square R. Interesting for us to understand is that this current that is flowing within the disk cannot shock anyone. The reason it cannot shock anyone is because the voltage that is produced over here, that is very much within the disk, and the current is happening within very much within the metal plate, and the current is flowing within the plate as well. So a person who is cooking, if they even touch this thing, they are not going to get a shock because currents are pretty much, the electrons are pretty much busy to compensate for their own movement. And these plates actually do not produce such a high voltage to give a person significant shock. They work with pretty low voltage, but because there are so many electrons available within a metal piece, even a small amount of voltage produced across the metal plate produces a huge amount of current. So we produce not so much of a high voltage difference that can possibly produce any health hazard for an operating person. The voltage produced is actually pretty weak, so person will never get a shock. Whereas because the conductor has so many free electrons present, it will produce a significantly high current even if there is a pretty small voltage. So the high current will produce a high amount of power or heating effect very naturally. So that's how this metal plate is going to become heated up within very short time, and you can put whatever you want to cook. You can put a cooking pot over here and definitely you can cook around with it. And this plate is basically going to work as your hot plate. And hot plate in this case means that this is the location where the heat will be available to you. So you use a metal pot of anything and you can put it over here. Important for you to understand that to cook properly, I shouldn't say properly, I should say efficient. To cook efficiently on this metal plate, it is important that you use a cooking pot that has a flat base, like a saucepan or a deep fry or a frying pan, something like this, something that has a round bottom. For example, like regular cooking pots of our country, this would not be doing cooking job within this place very efficient because the contact would be within a very small space. So the conduction process cannot be very effective. So you would be, it would take a long time. So it's better, other than this, it's better if we use a flat base so that the heat conduction is pretty well and you can cook it pretty fast. So that's another way how we can use eddy current to produce heating, which is pretty commonly used for cooking purposes. And the idea over here is that different locations of the conductor is experiencing different rate of change of magnetic flux linkage, which induces different values of EMF, and that produces eddy current within the conductor, which changes as and this is only happening because of the alternating magnetic field. Please try to understand one thing. If we did not produce an AC supply over here, if we did provide an DC supply over here, would this thing happen at all? Try to think. যদি আমরা আমাদের কয়েলে ডিসি সাপ্লাই দিতাম তাহলে কি হতো? 0 থেকে ম্যাক্সিমাম হওয়া পর্যন্ত সে একবার আমাদের কারেন্টটা ইনক্রিজ করতো. The current would only increase one time, and then the current will maintain a fixed value. So if we draw the current versus time graph, it will maintain a fixed value. A fixed value producing means we'll have different amounts of magnetic flux linkage in different places, but that flux linkage would not change over time. I mean, we'd have different values of flux linkage. Phi would be different in different locations because of the concentration of the magnetic fields are different, but there would be no del phi over del t. That would not happen because over the time, the current is not changing, so the magnetic flux linkage will also not be changing. So this circuit can never work using a DC circuit. And this will only work exclusively by an AC supply. The change of the supply current will cause in the change of the magnetic flux linkage that will in due process produce the eddy current, thus produce heating for necessary cooking process. Questions? Before I take other questions, Ifat, do you have your question answered at this point to some extent?
Sir, এখানে এই যে হিট এনার্জি প্রডিউস হচ্ছে ওটার অরিজিনাল সোর্স কোথায়? এই যে এসি কারেন্টের ইলেকট্রিক্যাল এনার্জি না?
Yes.
So ওইখানে kinetic energy হবে কেন? Why not the electrical energy of the current?
Oh, this is pretty simple. This is because I mean, try to think of it in a exclusive principle. For example, let's say we provide this current through this coil, but we do not move this disk at all. We will keep this disk stationary. Would you have eddy current produced? Think about it. You're gonna have a fixed amount of magnetic field over here, but the disk is not rotating, so the electrons are not cutting across this location region over here. Electrons are not cutting over here. You have, if the disk is stationary, the magnetic field is there. Would you have eddy current?
I mean, not if it's a DC current, তাহলে তো হবে না.
No. Yeah, if we do provide a DC current, yeah, that's my point. That if we do provide a DC current, exactly. My point is that we are providing a DC solenoid over here. We are providing an uniform magnetic field, not varying magnetic field, but we are not rotating that disk. In that case, we cannot have SA, cannot have eddy current. Comes to the point that the eddy current was produced because the electrons were moving. The electrons were moving by virtue of the kinetic energy of the disk. It is very much like, sort of like, in other words, I can say, it is a bit convoluted version of a basic generator. What happens in a generator that we have loops of wire which we have designed for our purpose, and the current is produced within these wires as we want. But what is happening over here, we are producing the current within a metal disk to flow through the metal disk on its own. So there is no definitive path of loop of current over here. So the current is allowed to flow through all the unaffected parts of that disk. But we are definitely producing current. So in a generator also, if you think about any generator, in a generator, we feed kinetic energy to the generator and we get out electrical energy of the generator. That's how generator works. In this case, in the same way, we are feeding kinetic energy to the system, which is producing electrical energy, causing the eddy current to exist. And that eddy current will naturally, almost immediately, converts into heat energy because of the resistance of the metal disk itself.
That's good. Thank you.
Clear হয়েছে কিনা? আচ্ছা, আমরা যদি complementary discussion, সেটা হচ্ছে what if we use the same device and provide an AC solenoid over here? What would happen at that point? Well, if we do provide an AC solenoid over here while the disk is also rotating, we would still be able to produce produce eddy current. The thing that will happen, that for 1/2 cycle of the, for example, let's say for 1/2 cycle of the coil, we will be producing a bigger amount of eddy current. For another 1/2 cycle of the coil, we might be producing smaller amount of eddy current. The idea is that if we apply an AC solenoid over here, try to think about it. This will change the magnetic field orientation, right? At some point, that magnetic field orientation is going to cause the electrons to experience a higher force in one way, and in the opposite direction is going to experience a lower amount of force. You are still going to have eddy current. Try to understand one thing. Should I say, electrons don't flow in a conductor like one by one. They all flow in the same way, like the marching of an army, or like the water flowing through a tube. Throughout the entire conductor, all the electrons flow simultaneously to produce the electric current. This is very important. I'll say it again. Throughout the whole conductor, all the electrons flow simultaneously to produce the electric current. So even if we apply an AC solenoid over here, the current will be back and forth. This specific direction that I've drawn, that one side of the, like in this case, my inside surface is positively charged and the outside surface was labeled to be negatively charged. We're not going to have that. What we're going to have is, we're going to have back and forth oscillating current within the disk, and that heating effect can still be achieved. So if we use an AC solenoid over here, it's also possible for us to produce eddy current. I did not use an AC solenoid over here for the sake of complicacy that I might not be able to transfer properly towards yours. ওই জন্য আমি এখানে আগে ডিসি সলিনয়েড দিয়ে তোমাদেরকে শুধু মোশন রিলেভেন্টটা বুঝাইলাম, আর এখানে আমি মোশন বাদ দিয়ে শুধুমাত্র এসি সলিনয়েডের জন্য কি হলো সেটা বুঝাইলাম। বাট ইফ ইউ কম্বাইন দিস বোথ ইফেক্ট, we can definitely produce eddy current as well. This should not be a fact that we cannot do that. We can definitely do that. মনে করো এই সিনারিওতেও ধরো, মানে this will not be very ideal for cooking. মনে করো এই সিনারিওতেও যদি আমরা এই কাজটা করি, যে let's say we are running this solenoid using an AC coil. At the same time, we have a mechanical way to oscillate this metal plate left and right, for example. তখন আমরা এখানে eddy current produce করতে পারবো. This plate would still heat up, but might not be a good utilization for cooking process, because you wouldn't want your cooking pot to oscillate like that. Might be difficult for us to handle. But would eddy current happen? Would we have the heating effect? Definitely yes. Very practical? Maybe not so. Are you good?
Yes, sir.
Beautiful. Thank you. Any further question from anyone else through the entire example of eddy current? These are the two practical examples that is included in your syllabus. So we are not going to discuss any further example, but eddy current can be used in a lot of different cases. The bottom line idea that you need to understand or remember for eddy current is that different part of a conductor is subjected to magnetic flux linkage at different rate, thus producing an EMF within itself in different location. So one part of the location would be having one type of EMF, the other part of the location have opposite type of EMF. So there would be a current flowing through the conductor internally, and that internal current is what we're defining as the eddy current. So what do we have to have eddy current? Different parts of a conductor piece should be subjected to different rate of change of magnetic flux change. Any further question?
স্যার, রেসিং কারের কি হচ্ছে তাহলে এডি কারেন্ট ইউজ করা যেতে পারে?
হ্যাঁ, রেসিং কারের ব্রেকিং এর জন্য আমরা এডি কারেন্ট ইউজ করতে পারি, বাট রেসিং কারের মানে we can definitely can, but the question is that compared to the conventional braking that they have, whether the setup of the eddy current use করতে হলে কিন্তু আমাদেরকে একটা significantly heavy একটা metal disc introduce করতে হবে, ঠিক না? এটার একটা certain amount of weight থাকবে. So a weight টা একটা important factor for any racing car. We can definitely introduce that thing. For example, that door figure that I drew over here, we can introduce an eddy current brake over here. It's very much possible, but whether it is convenient for other factors like the overall mass of the whole car body and the balance for turning and everything, those other factors are also important. As far as I know, cars don't usually use eddy current for braking. I mean, for high speed braking, they use the wind brakes which come from the spoilers. So there's these spoilers that they have, they can sometimes go more vertical or less vertical through hydraulic actuators. So those spoilers, the rear end spoilers, they usually come in more effect in the high speed other than eddy current. So eddy brakes can be introduced in high speed car. It's very much possible, but as far as I know, no automobile company have introduced them. But I know for a fact that eddy brakes are definitely used in magnetic levitation trains.
Okay, sir. Thank you.
No problem. All right. The next thing that we're going to see in today's class is RMS current. You guys know what this acronym means? Can somebody tell me?
Root means square.
Root means square. Beautiful. We have come across this term also in ideal gas situations where we were trying to define the behavior of ideal gas. Okay, RMS current. Let me first give you the concept of this thing, then I'm going to show you how the calculations are done. And there is a bit of a small jump over here in terms of skipping some calculation. I'm going to also show you that. The definition of RMS current goes like this. The amount of heating effect that an AC creates in a resistor, the amount of heating effect that an AC creates in a resistor, that same effect, if can be created by a DC, comma, if that same heating effect can be created by a DC, comma, that DC is said to be the RMS value of that AC. কিরকম আমি সব বুঝাই। মনে করো একটা এসি সাপ্লাইয়ের কারেন্ট ভার্সেস টাইম গ্রাফ হচ্ছে এরকম। এই এসি সাপ্লাইটাকে আমরা একটা ফিক্সড রেজিস্টারের মধ্যে দিয়ে ফ্লো করলাম। Let's say a resistor value হচ্ছে R. We're gonna flow this AC over through this R for a duration of T. এরপর দেখা গেল যে মনে করো আমাদের over this duration আমাদের total 200 joule heat produce হয়েছে। I'm just choosing a random number. এখন এখানে যতটুকু টাইম আছে আমার কাছে টাইমটা হচ্ছে 2 মিনিট, লেটস সে 2 মিনিট রান করার পর 200 জুল হিট প্রডিউস হয়েছে। সেম অ্যামাউন্ট অফ হিট সেম অ্যামাউন্ট অফ টাইমে প্রডিউস করার জন্য আমরা যদি এই সার্কিটটাকে এখন অফ করে দিই, দ্যাটস উই আর ইন্ট্রোডিউসিং আ সুইচ ওভার হিয়ার and we're going to introduce a DC supply over here using a closed switch. Let's আমরা এখন একটা DC সাপ্লাই দিয়ে এই কয়েলটাতে জিনিসটা করব। এখন কতটুকু ডিসি কারেন্ট দিলে থ্রু দ্য সেম রেজিস্টার আমরা সেম হিটিং ইফেক্ট পেতে পারবো, মানে হচ্ছে we're going to produce within a duration of 2 time we're going to be still producing a 200 joule of current, joule of heat energy. ওই ডিসি কারেন্টের ভ্যালুটাকে আমরা এসি কারেন্টের ইকুইভ্যালেন্ট আরএমএস ভ্যালু বলতেছি। এটা হচ্ছে ডেফিনিটিভ টার্ম। ডেফিনিটিভ টার্মটা হচ্ছে এরকম, ডেফিনিশনটা দেওয়ার জন্য আমরা হিটিং ইফেক্ট আদি ডেফিনিশন দেই, বাট এটা সবসময় হিটিং ইফেক্টের জন্য যে অ্যাপ্লিকেবল ব্যাপারটা এরকম না। So we use the heating effect to define this term. That's how the scientists did it, but it's not essentially relevant to heating effect. If we want to give you a bit more broader sense, try to have a look at this idea. Current is flowing in an AC supply back and forth. So if you want to measure the total amount of charge that flows through a conductor at any point, because it is flowing back and forth for any number of full cycles, that Q would be 0. Am I correct or not? Let's see, if I take one cycle, what is the total amount of charge flow through this resistor after one full cycle? For the same amount, for half the time the charge flows this way, for half the time the charge flows that way. So the total amount of charge, I mean, if I do the some amount of charge flow would be 0, because the charges are flowing in opposite direction if you consider it that way. So it might give us the idea that AC is actually not making any charge flow, because we also know that V equals to E over Q. So if we want to subject the energy E, energy is given by voltage into current, voltage into charge. So if for any full number of cycles the charge amount is 0, essentially that multiplied by the voltage gives us 0 energy. So that's not a very convenient way to represent that, because that would propose that AC supply is not doing any energy transfer whatsoever, but that's not the case. AC supply does provide energy. So the idea is that the amount of energy transfer that we have, if that same energy transfer can be made available by a certain DC supply of a fixed value, maybe that value is over here, we're going to label this thing. This is what we're going to define as IRMS. How do we calculate this thing? Let me show you. Let's say this is the I versus T graph of a AC supply. Let's say this is how it looks like. Not so good, but bear with me. This is I versus T. I versus T. If I want to square this graph is going to start to take a shape like this. I'm just squaring it to give you a bit of an idea. It's going to start to look like this. Why am I squaring it? I'm kind of getting back to it. I'm going to tell you in a while. So I square is going to look somewhat like this. Curves all the way. No kinks. This is how the I square looks like. If I multiply R with this same graph, let's say R equals to 1. I'm just choosing 1 because I don't want to draw a new graph. So this same graph can be also labeled as I square R. And we have the power on the graph of the red graph, that is I square R. We have the T. So if we want to measure the total amount of energy transfer up to this amount of time, let's say within this part of the circuit, we just have to find out the area under the curve, because area under the curve will necessarily give you what? I square RT. That's basically an expression of energy. বুঝো পোলাবান I square R হচ্ছে কি power into time gives you what? Energy. So if we want to measure the total amount of energy transfer through the AC supply over this up to this much point, we might as well have to integrate this thing logically somehow and measure the total amount of area that is underneath this red curve, and that will give us the total amount of energy transferred within this amount of time. It logically understandable kina? I'm just theoretical আলাপ করতেছি। হ্যালো, আমার কথা শোনা
টির কি হলো?
হ্যাঁ হ্যাঁ বলো।
I square আর টি আচ্ছা না টি এর কি হলো তাহলে?
ওই যে টিটা আছে দেখে তো আমি ইন্টিগ্রেশনের কথা বললাম। ইউ আর ট্রাইং টু ফাইন্ড আউট দ্য এরিয়া।
ও আচ্ছা হ্যাঁ, ও হ্যাঁ বুঝছি।
ঠিক আছে, এখন জিনিসটা হচ্ছে এই সবগুলা এই বাম্পের এরিয়া ক্যালকুলেট করার পর টোটাল যে এরিয়াটা হবে, the total area that we're going to calculate out of all of this all of this area under the curves, if we can somehow represent that total area within the same curve using a perfect rectangle. So let's say this is the rectangle, ash color rectangle. I'm going to label it like that. That has the same area as all the blue areas. We can have that as well for the same amount of time, this much area and the blue area. So what I'm trying to represent is that the hash area of this, sorry, I'll do it this way. This is exactly equal to the hash area of blue. We can draw a rectangle like that. That rectangle will definitely have a cutoff at the y-axis. So this is the value that we are defining as RMS value. In this case, this would be I squared RMS because we are producing this. We are producing the energy. So in this case, if we use this whole rectangle thing, that would be I RMS whole square into R into T would give us the same equal amount of energy. So practically what I'm saying is that if we just flat down or if we squash all of these plateaus to a flat land, the amount of area that we're gonna get. এটা ক্যালকুলেট করার কিছু লজিক্যাল উপায় আছে। লজিক্যাল উপায়টা হচ্ছে that we can actually we can use integration, steps of integration to find out how much area does this cover and then how much area should this cover for equal area. That integration calculation is not introduced in the syllabus, so I'm not going to bother you for that. If you are interested, you can look up for it in the internet or can ask me. I could guide you towards some sources. For our syllabus, what all that we are introduced is that if a certain for a certain circuit, if the for a certain AC supply, we have the max value and we have the RMS value. So if I just try to draw another graph, let's say for an AC supply, if we draw it to draw V versus T, and this is the AC supply that we get, this is what we define as the Vmax. Sometimes it is also labeled as V naught. So if this is the maximum voltage value, the RMS value, VRMS, is equals to Vmax divided by √2. In the same way, we can also calculate the IRMS for any circuit. IRMS equals to Imax divided by √2. এই √2টা আসে হচ্ছে ইন্টিগ্রেশন থেকে ক্যালকুলেশন করে, ওই ক্যালকুলেশন তোমাদের সিলেবাসে নাই, ওই জন্য আমি ইন্টিগ্রেশন তোমাদের দেখাচ্ছি না। ইফ ইউ ক্যান রিমেম্বার দিস মাচ, ইউ আর গুড টু গো। সো এটা হচ্ছে একটা সার্টেন সেট অফ ফর্মুলা যেটা আমাদের কাজে লাগবে। And one more thing that I would like to tell you is that typically for any device or for any supply equipment, the voltage that is labeled on the device, for example, if we know that our households in Bangladesh, they are supplied with 220 volt AC. That's a very common thing. We are supplied with 220 volt AC. This 220 volt AC actually is the RMS voltage of the supply. It's not the peak voltage, it's the RMS voltage. So this, if you are trying to calculate the power output of any device, then you can directly use this calculation, or and you would be good with your you get the proper kind. For example, if a device is labeled as 220 volt AC, 1000 watt, then you can pretty much calculate that what would be the resistance of this device by simply doing P square by R, P equals to V square by R, and you can also calculate how much power it takes. I mean, this value can be used for all the calculation, but this does not represent what would be the maximum voltage of the supply. The maximum voltage for a 220 volt RMS AC supply, Vmax would be If you just have a look over here, if you just multiply root 2 on the other side, we get the Vmax. So Vmax would be root over 2 multiplied by RMS. So that is going to give us about 0.707 multiplied by 220. না ভুল লিখছি। root 2 হচ্ছে কত 1.21 কত জানো? দেখো তো এটা মাল্টিপ্লাই করলে কত হয়? root over 2 multiplied by 220 করলে কত হয়? 431 মনে হয় আসার কথা। Someone help me. I don't have calculator. Or do I have?
$311.
311. Nearly 311. So what this is going to show us is that if a person gets a shock out of a 220 volt supply, they are not going to get a 220 volt maximum shock. Their maximum shock experience would be equivalent to 311 volt. And this is very important. This is also the reason, for example, whenever we have some high cables in the poles, which has, for example, the high tension cables, we call them, they have, let's say, 1000 volt. These are not supplied to household. They go through a transformer, become smaller by the transformer mechanism, and that's how they and then they are transferred. But if a certain cable in the transmission line is labeled as 1000 volt, this cable is not actually carrying 1000 volt maximum. This 1000 volt is the RMS value of that thing. So the device actually carries about maximum voltage of about 1400 volts. So if a person gets a shock, or if a crow or a bird gets a shock out of those high tension cables, they actually receive a much bigger amount of shock from the high voltage values. So that's why it can be more deadly.
স্যার
হ্যাঁ বলো।
স্যার আমি না VRMS আর IRMS দুইটা ডিফারেন্স বুঝিনি, মানে দুইটা বুঝিনি আলাদা করে।
ও এই দুইটা আলাদা কোনো ভ্যালু নাই, সেটা হচ্ছে যে আমরা যদি ভি ভার্সেস টি গ্রাফ আঁকি, সো ভিম্যাক্স এর ভ্যালু যদি এখানে হয়, ভিআরএমএস এর ভ্যালু এরকম কোন একটা জায়গাতে হবে। ভিম্যাক্সটা হচ্ছে আমাদের কার্ভ করে দেখানো, whereas the VRMS can be represented as a simple horizontal line, as if it's a DC supply. So our VRMS or IRMS relationship is very simple. For example, we know the equation ohms of V equals to IR, right? So this equation can be rewritten for max value. This same equation can be rewritten for RMS value. For example, I can write for Vmax equals to Imax into R, or VRMS it would be equals to IRMS into R. এই দুটো ইকুয়েশন হচ্ছে basically V equals to I written for two different expression. However, in certain cases আমাদের অন্য ভ্যারিয়েবল গুলা রিকোয়ারমেন্ট অনুযায়ী এই ইকুয়েশন থেকে আমাদের চেঞ্জ মানে রিপ্লেস করতে হতে পারে, সেটা ডিপেন্ডিং অন দ্য কোশ্চেন হোয়াট টাইপ অফ ভ্যারিয়েবলস ডু উই গেট। সো ভোল্টেজ হচ্ছে আমাদের voltage is the reason of the current flow, and current flow is the outcome of the voltage supply and the resistance of the contactor. Current flow is basically the dependent output. So current can be also defined the same way. So if we have within a circuit, within a graph, current versus time graph that looks like this. So if this is our Imax value, and IRMS would be somewhere around here. Max value basically represents what is the peak value of the DC supply. If you don't want to define it as max, you can also define it as peak, I peak, or V peak, the top value magnitude wise. Does that answer your confusion?
No sir, মানে এখানে তো দুইটা না আমি আসলে বুঝছি না, মানে দুইটা ইকুয়েশন ইকুয়েট করলাম কিন্তু দুইটা তো আলাদা ইকুয়েশন, মানে আর না নেই এখানে।
আচ্ছা এই ইকুয়েশন আর নাই তো? হ্যাঁ না না না, this equation is just showing you that what is the ratio between these two values. মানে হচ্ছে Vmax হচ্ছে, মনে করো Vmax এর গ্রাফে যদি লেবেল করি, Vmax টা হচ্ছে এইটুক বড় আর VRMS টা হচ্ছে এইটুক বড়। সো এই দুটোর মধ্যে নিউমেরিক্যাল রিলেশনশিপটা কতটুকু? নিউমেরিক্যাল রিলেশনশিপটা হচ্ছে √2 রেশিও। এই √2টা একটা ইন্টিগ্রেশনাল ক্যালকুলেশন থেকে আসে, যেটা তোমাদের সিলেবাসে নাই দেখে আমি দেখাই নাই।
স্যার এটা না কনফিউশন না, মানে এটা বুঝেছি কিন্তু iMac তো হচ্ছে আলাদা না?
হ্যাঁ, Vmax and Imax definitely different from each other. Vmax and Imax are not the same thing. V হচ্ছে voltage, I হচ্ছে current, and these two variables are related by this equation. But both the RMS and the maximum value are related by this √2 ratio. মানে VRMS, IRMS are not the same thing. Vmax and Imax are not the same thing. The relationship between VRMS and Vmax is this one, and IRMS and Imax is related by this equation. They are not the same thing, but they have the similar relationship.
What, স্যার এখন বুঝেছি।
বুঝছো? For example, if I put it this way, let's say your grandparents have children which are your parents have children which are you. So there is a parent-children relationship between two generations, but this doesn't mean that your grandparents and you are the same people.
Yes, স্যার বুঝেছি।
Beautiful. আচ্ছা, আরেকটা জিনিস আমি আগে ডিসকাস করতে ভুলে গেছিলাম, আমার মাত্র মাথায় আসছে, সেটা হচ্ছে ইফাত একটা জিনিস আমাকে বলছে যে আমাদের যদি এডি কারেন্টের জন্য কারেন্ট লস হয় তাহলে ট্রান্সফরমার কি একই রকম সমস্যা হওয়ার কথা না? ইফাত, রিমেম্বার? Ifat left. I think he has another class. Okay, I'm just gonna cover that discussion. The answer is yes. The reason transformers sometimes fail in our country, it happens quite often, is because they get too much heated up because of the eddy current. Transformers also experience eddy current loss within themselves. And there is practically no way to make the eddy current loss to become zero. What I'm trying to say is that if I try to show you a very basic design of a practical transformer, I mean, the very simple design of transformer that we have come across can look like this. We have a soft iron core which is laminated. We have the primary coil going around over here. We have the secondary coil going around over here. For example, in this case, I have drawn more coil turns on the secondary coil. So this is a step-up transformer. So this transformer can work. The other version that we have seen, that we can have a closed loop. So this is an open loop core. We have this end open, this end open, or we can have a confined iron core which can be rectangular. In some other cases, we can also make this circular for if we want. The core can be also designed to be circular, and we can provide primary coil on one side and secondary coil on the other side. That can also work. So this is also actually a transformer. So this can also work. So for all of these cases, whenever this transformer happen, you have to understand that when the primary coil produces the current through the coil, and it is an AC supply importantly, so this part of the conductor is subjected to the magnetic field induction more strongly compared to the other parts of the magnetic field induction, which definitely produces a current within the soft iron core. The current that produces within the soft iron core is basically what the eddy current is. That eddy current heats up the soft iron core, and if we want the transformer to run properly, we have to significantly cool down the eddy current. And whenever the coolant that we use, typically all the transformers that we have, they are dipped inside an oil bath, and the oil is usually cooled down by natural convection process through fins and channels which exist outside the transformer body. For example, if I just try to show you a figure for a transformer, interesting things happen when you put transformer as a search key in the Google. You don't get a transformer, you get the transformer movie transformer. So have a look, transformer. Oh no, we get the real transformer. Good. What? Oh, acha. In special search, you get the optimus panel. Beautiful, beautiful. So if you just have a look at this transformer, so this is a very basic view of the transformer. This rectangular box that is inside it, that is actually where the transformer body and the coil surface. All of these fin-like structures that you're seeing, these are actually, for example, right over here, and they are over here. They're over here. Some other transformers can have other type of convection current designs. For example, this one, have a look. This is the cooling tank conservator tank. These are all physical pathways, channels through which the cooling can happen. So the soft iron core, inside this middle rectangular box, which is defined as a main tank, inside this thing we have this actual heating element, the soft iron core, which heats up. naturally the hot oil goes up, and then they travel through these tubes, and then they cool off by leaving heat through this rectangular channel type of things, and then they fall down through this thing, and eventually they go back to the tube. So the oil is naturally cooled off by using the cooling tubes. Now, whenever the oil becomes old enough, sometimes they dissociate and produce particulate carbon, which can sometimes clog up these pathways, and the conventional current cannot happen as much as it should for the effective cooling of this thing. And that way the transformer device can slowly start to heat up, and at one point, if it cannot handle that pressure, it goes off, boom. It actually doesn't produce an explosion, it simply disconnects the circuit and somehow stops the current in a way. These devices are designed in such a way that they will fail in a way that they will not do their job anymore, but they will not disassociate, because if this hot oil actually goes into burst like a bomb, that would be a huge massacre, massively dangerous thing, because they are always installed in populous areas, beside buildings, and on overhead positions for pedestrians and road vehicles. So they have safety systems which stops their operation if they heat up too much, but they do not actually explode per se. So transformers also experience eddy current. They are designed so that they would produce the least amount of eddy current. The most practical transformers that we use in today's world actually have overlapping wires. So they actually look somewhat like this. We have maybe soft iron core that looks like this, and underneath the core we have the secondary coil, as far as I don't know, I might be wrong. And this is, the core is coated, then an insulated secondary coil is introduced, and over that secondary coil we produce the primary coil. So they are both wind over a single structure. This is done to reduce the eddy current as much as possible, but it never reduces to zero. So all transformers do have some eddy current loss, so it's definitely a problem. আচ্ছা, এটা গেল হচ্ছে এইটুকু পর্যন্ত ডিসকাশন। বিয়ন্ড দ্যাট, আচ্ছা, আমি তোমাদের ওয়ার্কশিট গুলো সব আজকেই প্রিন্ট দিব। হোপফুলি তোমরা কালকে এগুলো পিক আপ করতে পারবা। জিয়ারাত, আমি তোমাকে ক্লাস শেষ হওয়ার পর মেসেঞ্জারে একটা মেসেজ দিব, তুমি একটু দেখো, ঠিক আছে?
আচ্ছা স্যার।
ওকে, আচ্ছা, এটা আমার বুকলে রান্না লাগবে।